Thank you to Delete Me for supporting PBS. Is there a limit to how much energy you can cram into or pull out of one patch of space? Well, we thought so, but the James Webb Space Telescope has found a quasar that simultaneously breaks a century-old theoretical limit and may also explain the conundrum of gigantic black holes in the early universe. There are black holes at the beginning of time that don't make sense. They are just too big. Black holes grow by consuming matter and merging with other black holes, in some cases growing into the supermassive black holes in the centers of galaxies, intermittently powering enormously bright quasars in the process. We see quasars as countless specks of light shining from the distant universe. As we've learned to peer deeper and deeper into the cosmic dawn, we expected to see quasars dwindle in power. Their black hole engines should be smaller the closer we get to the Big Bang. But we've now found quite a few quasars from the first billion years that are way too massive to have grown by the mechanisms we think we understand. The James Webb Space Telescope is only finding more, and we're forced to rethink our understanding of black hole formation and growth. There are two broad ways to grow an oversized black hole in the early universe. Either black holes started out uncomfortably large from colossal early stars and then fed almost continuously for a billion years, or black holes managed to consume material much faster than we thought possible. Although Webb is finding uncomfortably massive early black holes, it's also finding clues to answering this conundrum. Take a look at this guy. LID 568, an active galactic nucleus recently observed with the Webb, is not the most massive black hole, nor is it the earliest at 1.5 billion years after the Big Bang. We found quasars hosting black holes 1,000 times more massive when the universe was half that age. But LID 568 is special because it's currently growing 4,000 times faster than the theoretical limit. We've seen quasars exceed the theoretical limit before, but nothing like this. If LID 568's earlier, bigger siblings did the same thing that it is, then we may be closer to understanding how those early black holes got so chonky so fast. But first, we need to actually believe that this black hole really is feeding as fast as it seems to be. So today, I want to talk about the absolute limits of growth and power in our universe. What's the most energy that you can both cram into and get
Fully
out of a
printed
patch
zero
of space?
static power MOS 2
The physics
switch.
we're going to explore will describe the most extreme environments around the most massive black holes in the universe, but it's also the same physics that first allowed us to understand something even more important: every star in the universe. We tend to think of black holes as
In
purely
contrast to
sucking.
previous works
They
based
drag
on
stuff in and spit nothing out. But actually, as evidenced by the quasar, black holes, or at least the regions around them, can be the brightest things in the universe. As matter falls towards a black hole, it heats up and radiates before dropping past the event horizon, the surface of no return. That radiation can blast back other infalling material, shutting off fueling of the black hole. The theoretical limit to the rate at which a black hole can feed is called the Eddington limit. It's an upper bound on both the rate of fueling and the power output in radiation, also called luminosity. At the Eddington limit, the pressure from the outgoing radiation exactly balances the strength of gravity. It seems like it should be impossible to feed a black hole any faster than the Eddington limit, or for a quasar to glow brighter than the Eddington luminosity. But LID 568 glows 4,000 times brighter than this, and likely grows at a similarly super Eddington rate.
nature.
The best way to understand how this is possible is to understand the origin of the Eddington limit. It's named after this guy. Now, when a science concept gets named after someone,
Scientists
sometimes
at the
they
university
deserve the credit, sometimes less so. But Sir Arthur Stanley Eddington and his limit are in the former category. This dude was the OG astrophysicist. He was supposedly one of the few who understood Einstein's general theory of relativity when it first came out, and he led the expedition to measure the bending of light around the sun in the 1919 eclipse, providing, in fact, the first verification of GR's predictions. Eddington correctly guessed that the source of energy in stars is the fusion of hydrogen into helium, and that was before we knew that stars are made of hydrogen. He pretty much founded the field of stellar physics, and this is where his eponymous limit actually comes from. That means to understand quasars at their limit, we need to understand the limits of stars.
We've never
Eddington's
been closer
reasoning
to
went
finding
like
life
this.
outside our solar
Stars
system.
are massive, therefore have very powerful gravitational fields, powerful enough to cause any fluid, such as a cloud of gas, to collapse under its own weight. Unless, that is, there's some outward push to resist the collapse. Stars are not typically collapsing, therefore something must
In
support them.
2025, we might
In
detect the
Eddington's
first signs of
time, the leading idea for that support was that stars were hot from the energy gained by the gas as it collapsed to form the star. For a gas, high temperature means high pressure, and that pressure resists further collapse. Of course, stars radiate their internal energy, so this support has to diminish over time. You might think that would leach away the star's support and so cause it to collapse, at least a little bit. But remember that collapsing converts gravitational potential energy into heat, so as a star radiates energy, it should also shrink and generate more heat energy to resist collapse. The result would be a very slow shrinking of the star. And in fact, this balance between gravity and gas pressure is what keeps stars supported and stable. But Eddington realized that such a star couldn't last nearly long enough. It would need another source of energy, and as I mentioned, Eddington guessed that it must be fusion. Eddington used this balance between gas pressure and gravity to figure out how the brightness of stars must depend on mass. As mass increases, higher pressures and temperatures are needed to support against the increasing gravity. And higher temperature leads to higher luminosity. Hotter things glow brighter, a lot brighter. Eddington calculated that the luminosity of a star acting as a pure ideal gas should increase with the cube of mass. In reality, things are a bit more complicated and the dependency can go as high as mass to the power of 4.5. Okay, this is our first effort at figuring out how luminous something can be. Stars for now, but all this stuff will...
Excuse me, do you mind? Everywhere else is full. Not at all. I'm Ron, by the way. Ron Weasley. I'm Harry Potter. So is it true? I mean, do you really have the what? The scar. Oh, yeah. Wicked.
Anything off the trolley, dears?
No, thanks. I'm all set. We'll take the lot. Whoa. Bertie bought every flavour beans.
They mean every flavour. There's chocolate and peppermint, and there's also spinach, liver and tripe. George sweared he got a bogey flavoured one once.
These aren't real frogs, are they?
It's just a spell. Besides, it's the cards you want. Each pack's got a famous witch or wizard. I've got about 500 myself. Watch it. Oh, that's rotten luck. I've only got one good jump in them to begin with. I've got Dumbledore. I got about 6 of him.
Hey, he's gone.
Well, you can't expect him to run around all day, can you? This is Scabbers, by the way. Pathetic, isn't he? Just a little bit. Fred gave me a spell that's to turn him yellow. Want to see?
Yeah.
Son?
Has anyone seen a toad? A boy named Neville's lost one.
No.
Oh, are you doing magic? Let's see then.
Sunshine, daisies, buttermellow. Turn this stupid fat rat yellow.
Sure that's a real spell? Well, it's not very good, is it? Of course, I've only tried a few simple ones myself, but they've all worked for me. For example, Oculus Reparo. That's better, isn't it? Holy cricket! You're Harry Potter!
Deletion
I'm
and
Hermione
silencing
Granger.
of human protein coding
And-
genes.
You are?
Ron Weasley.
Pleasure. You two better change into robes. I expect we'll be arriving soon.
Hooray, CRISPR libraries extend the scope of gene perturbation screens to non-selectable cell
You've got
phenotypes.
dirt on your nose, by the way. Did you know? Just there.
Library generation.
Bye bye.